Jordan, you're muted.
Yeah.
Oh, yeah.
Cheers. Okay. Let's just get this screen going. Okay, so my name is John Pitt, and this is my talk on model predictions of overwash extent to the marginalized zone. This work was done in collaboration with Luke Bennett, with both of us being at the University of Adelaide and supported by the ARC. So we're going to start by defining some of these terms, in particular marginalized zone and overwash, and then look at the model predictions. So I'm sure we're all probably pretty familiar with the marginalized zone now, but here's an example. So we have these chunks of sea ice called flows and a slurry of ice between the flows. And this is, in this particular example, the marginalized zone is due to the wave action, breaking up, stopping the consolidation of the ice into a thin sheet, a continuous sheet. So the interesting thing about the marginalized zone is that it's interacted by waves, as Alberto pointed out yesterday, and we're actually taking a photo from him. And we can see these waves out here on the horizon, and they're even on the ship itself as well. So we're very much interested in trying to understand the interaction between the sea ice that forms in the marginalized zone and the ocean waves. So the phenomenon we're focusing on today is overwash. So here's an example of overwash from an experiment where we have a wooden disc floating on this water, and the water is able to, under the right conditions, push itself up onto the top of the disc, overwashing it. So we have a bit of overwash here on the left and a lot of overwash here on the right. So what is the importance for overwash on the interaction between the marginalized zone and ocean waves? So the occurrence of overwash is dissipating wave energy from the ocean waves. Likewise, the appearance of water due to overwash on these flows that make up the marginalized zone can lead to accelerated growth or melting, depending on the surrounding temperature. So we know it is a component, and we're very much interested in finding out what its effect is, particularly at the field scale. So because of this, there's been a lot of lab work on overwash, and it's very common in lab work to see overwash, to the point where people have built barriers on their model flows to try and stop it from occurring. However, in the real world, there's a real lack of real-world observations of overwash occurring. And so the goal is basically to take what we've learned from lab work and theory and try and make predictions for the real world and provide an extent of overwash into fields of ice to facilitate and motivate people to go out and make some real-world observations. Although those videos look pretty good, so maybe we'll get something out of those. Okay, so here's our model at a very conceptual level. And basically, the idea here is that to understand the overwash of the entire flow field, we need to understand the overwash of the individual flows that comprise it. And we're going to focus mainly on this overwash of a single flow model, and then kind of just take the multiple flow extension for granted almost, but I'll discuss it a little bit. So what we want out of our model is to take the properties of the single flow, in particular for this 2D model that we're interested in today, is just going to be the geometry, which is its thickness and length, and then also its density, telling us how deep that flow is sitting in the water, as well as some properties of the flow rate's response to forcing, such as the Poisson's ratio and the Young's modulus. And then we want to throw some incoming waves, in particular an irregular wave field defined by a spectra. I'm sure most of you, well, we're all wave people, so I'm probably very familiar with the spectra. But basically what we're trying to do is describe the distribution of wave energy over the frequencies. This is one particular spectrum, particularly the John-Swap spectrum, with a significant wave height of 0.02, measuring the total amount of energy in the spectrum, and the peak period of 0.8, telling us where that maximum in the spectrum is occurring. And since we've plotted against angular frequency omega, this is actually occurring at 2 pi on tau p there, as you can see. So each one of these dots represents a frequency component with an amplitude corresponding to the spectrum. And this gives us these frequency components, but there's actually a lot of them, as you can see from the blue dots here, and indeed infinitely many if you want to make the full continuous approximation. And from that, we can produce our real sea surface, a sea surface realization using random phase differences between these frequency components. And here, this sea surface realization is those from the approximation of the blue dots, not the full spectrum. But we get a pretty good approximation to real ocean states in this way. And this is one particular case, and I've drawn the significant wave height to show you how it's kind of measuring the total energy. In particular, it corresponds nicely to the mean of the highest 1/3 of waves in your time series. So what we want to do is take our spectrum, incoming wave spectrum, and produce spectrum at the left and right edges of the flows but instead of being relative to the still water line, which the regular spectrum is, it's going to be relative to the flow's motion at the left and right edges. And we're going to call this SL for S left and SR for S right. So our model of coupled flow wave motions look like this. We have our Z axis being vertical with its 0 at the still water line, and our X axis being horizontal with its 0 at the flow. The flow has a length D and a thickness H. The water is capital H deep. And our freeboard is given by the Archimedean drafter related to the relative density of the flow in the water. And this freeboard is FB. Our model is thin plate for the flow's motion. So it's a linear problem for the thin plate, and a linear potential flow theory telling us how the water moves. So everything's linear. This spectrum is going to make sense for this linear model we've developed here. And when we chuck a method at it, such as Nicholas just described, or as I've cited here from Luke's work, then we can get solutions to the incoming wave problem to this flow. So we have our incoming spectrum, S of omega. I've drawn a realization to just show you what the irregular wave field would look like for one realization. And then the left spectrum is given by the incoming wave spectrum times this coefficient, which is given by the solution of methods such as the one cited here. And it depends on the flow, the wave's motion, the water motion, which is captured by 1, the incident wave, plus the reflection coefficient, which depends on the incoming wave frequency, and then take the flow's motion. And so that makes it relative to that flow's motion, which is why it's got that dot here. That's the point it's relative to. So it's moving with the flow up and down, and it's measuring the C state relative to it. Likewise, at the right edge of the flow, we have our incoming wave spectrum again, with a coefficient that depends on the transmitted wave, T of omega, take the flow's motion, which also depends on the frequency. But using this method, you can solve for each of those components of the frequency component and get out an approximate spectrum to the solution, and thus describe the coupled flow and wave motions, which we can then use to make some overwash predictions. So what we can do now is develop a frequency of overwash given by the spectrum, described in the ensemble of all the possible random phase C states described by it. So this is a contribution, so I've highlighted it here in red, and it's also the important point, I guess, the output of this overwash model. Okay, so from our spectra, for any spectra, we can find the mean time between waves above the flow edge by a small amount epsilon. And at the left and right, SL and SR, this is going to correspond to the mean time between overwashing waves. And this is given by a theory such as Rice here. So we have our mean time between waves above that flow's edge plus a small amount epsilon, which is a millimeter, is equal to this right-hand side, which just depends on the spectral moments of the relevant spectra. So at the left edge, it's going to depend on SL, and at the right edge, it's going to depend on SR and the freeboard height as well, and that's mold tolerance, epsilon. And then by comparing the different mean wave periods we have, in particular, the mean wave period for the incoming waves at the left edge and the mean overwashing waves at the left edge and the mean time between overwashing events at the right edge and the mean incoming wave periods to the flow, we can define a overwashing frequency. And I just take it to be the maximum of the overwashing frequency at the left edge and the right edge, since we're kind of just edge agnostic from this point of view. And then to determine if overwash is occurring, we just set some tolerance on our frequency of overwashing to determine whether it's rare or not rare, essentially. So we predict overwash if that overwashing frequency is above this F tolerance, which I chose to be 0.05, and otherwise overwash is not predicted. Okay, so we have an overwashing model which just tells us if a single flow is overwashing with above some frequency. And this frequency in particular corresponds to, you'd expect overwash to occur once, at least once, in 20 mean wave periods. And the reason we've tied it to the mean wave period is because we want to be able to compare different incoming wave periods consistently with the same tolerance. Okay, and then to extend it to multiple flows, we need how the flows are going to change inside my MIS, or my marginalized zone. So this is things such as Nicholas pointed out, the flow size distribution, but you can also think about thickness distributions as well, although we're just sticking to the flow size distribution today, and we won't really discuss it. But from that flow size distribution and other MIS properties, you can define the attenuation inside your MIS, which just gives us our spectra at each location or each distance into the MIS. So it's going to look something like this. So we have our model MIS, it's 3 flows, and what we want is an incoming wave spectra to the flow field, which is that spectra I showed before. It's transmitted by that first flow, and then we can define the incoming spectra to the second flow, S of omega 2, because it's at 2 meters, and then S of omega 4 to the third flow. And so we have this spectrum at any distance we want. Now, given our spectra at any distance we want and our overwashing of a single flow, we can determine the extent of overwash in the MIS by looking at the overwash, the spectra at a location and the individual flow properties there and determining the extent of overwash. So great, but does it work? Well, here's an experiment that we're going to compare it to. So in this experiment, waves are generated at the left edge of the basin and then travel from left to right through this array of wooden discs, which I showed a photo of before, which are the brown circles, and then are dissipated by the beach. And fortunately, they were captured by cameras, which are these red squares, which have a field of view highlighted here, allowing us to make observations of overwash in the experiment. Now, you'll notice that I did a 2D model, and indeed, we're going to make a 2D prediction in the direction of the wave propagation, which is just the 3 discs, the maximum that we can have. So, for instance, just these 3 discs or these 3 discs. We're just going to make a prediction there. And what we're going to do is describe these predictions in terms of different incoming wave spectra. So we have on the vertical axis a significant wave height for our John Swab spectrum, which we use, which I showed before. And on the horizontal axis, we have our peak period for that John Swab spectrum. And so each point in this plot is one incoming wave spectrum, and then we make an overwash prediction for the experiment. And that gives us this plot with the colors corresponding to the number of discs overwashed. In the blue region, we have no discs overwashing. In the red region, we have the first disc overwashing. In the green region, we have first and second disc overwashing. And in the orange region, we have all 3 discs overwashing. That's the prediction. Now, the interesting effect here is the period dependence. So for very low periods, high frequency waves, most wave energy is reflected. And what this means is you get an increase in the wave field before that initial flow due to reflection, which allows for a very easy overwash, or not very much significant wave height required to overwash that first disk. But because most wave energy is reflected, that overwash doesn't extend far, since it runs out of energy very quickly. And so we can see that the red region expands out very quickly. Conversely, for long period waves, low frequencies, most wave energy is transmitted easily. So we don't get a very significant reflection of wave energy, which means we need more significant wave height, more wave energy to overwash that first disk, but then not much more, since most wave energy is transmitted to extend that overwash further into the flow field. Now, our observations, there are 3 experiments, and in all 3, there was some overwash. In 2, we had 1 disk overwashing, and they sit here, precisely in the red region that the model predicts. So good. And in the 3rd experiment, we had all 3 disks overwashing, and that sits right in the orange region as well. So pretty happy with that. I will also point out that we did do regular wave experiments as well to get more than just 3 points of validation, and they also agreed pretty well. So seems to work. Now, I guess the goal is, can we make some predictions in the real world? Well, luckily, Alberto already went before me, and he was on this voyage, the Argylhouse 2 voyage from the South African icebreaker, and it traveled into the MIS around Antarctica and around the Weddell Sea, and took this path from the open ocean down into the MIS and looped back around itself. And this is a plot of the ice concentration there. So you can see the MIS being in the dark red and the open ocean being in the very pale blue, but dark, or very like matte. So the interesting thing about this particular voyage was that there was a polar cyclone nearby that created very strong waves, and they were able to observe waves very deep into the MIS, very large waves. And this is kind of ideal conditions to get overwash, since we have a lot of wave energy. And so this is quite a nice example for making a prediction. So what we're going to do is basically take transects and use the ice concentration data that we have, the MIS properties that we also have for this experiment, of this voyage, and the wave properties that we have as well, and make some predictions of overwash. And that looks precisely like this. So each dashed line is a transect in the mean wave direction, and we draw it out to its predicted extent of overwash. So this is the region of overwash extent, is all those dashed lines together. And we can see that overwash does not penetrate very far into the MIS and really is stuck at the edge. Not really bounded by ice concentration per se, because we do get significant ice concentration of about half at the very edge here, but it's quite limited because the attenuation through the ice is so strong, particularly for those higher frequencies that are driving the overwash. And so we've achieved our goal. We can do what we set out to do, which is great. So thanks.
Thanks, Jordan, and thanks for keeping really well to time. So I've got time for a couple of questions.